All right, so again, we're talking about vibrating bonds. And so we can actually model these bonds as a spring, which acts kind of as the bond here, connected to two balls, which are the atoms here. And so there's going to be two main factors that determine the IR absorbance, or basically how hard or easy it is to vibrate this spring or stretch this spring out. The first is going to be the mass of the atoms. And then the second is going to be the bond strength. All right, so if we draw our little ball with our spring, right, that's our model. And then the absorbed frequency that this will occur at is going to be proportional to this equation right here. You don't have to know this equation at all. It's 2 pi over c. This is equal to F over m reduced up to the 1/2. F is the force constant. That's related to your bond strength. And this m sub red is the reduced mass. And so what this allows us is to treat the two masses of the balls as one. So we do m1 times m2 over m1 plus m2. And so we don't really care too much about this equation, but we just want to point out two things here. We see that F, the force constant, is in the denominator. And so as we increase the bond strength, we increase the frequency at which it will absorb. And so that means that strong bonds will absorb at high energy IR. And then on the, and so you can see this as an example. You can see a carbon triple bond, carbon double bond, and then, or carbon nitrogen triple, double, and single bond. This occurs at around 22 inverse centimeters, which is just a way of saying frequency. 1600, and then 1100, right? So you can see as the bond gets weaker from triple to single, the frequency goes down and vice versa. The second part we notice about this equation is that the m reduced part, the mass part, is on the denominator, and so it's going to be inversely proportional to the frequency of the light absorbs. And so the way of saying that is, as the mass is increased, the frequency at which it absorbs will decrease, right? And that's lower energy light is being absorbed, right? And so you can compare this to like a CH, a CD, or maybe a CCl. As we go towards the right, we get higher and higher masses, right? So this is about approximately 3,000. This is approximately 2,200, and it's approximately 700. All these units are inverse centimeters. And so you can tell you a lot about a molecule based on its IR frequency. And if you take some kind of computational modeling class, they'll have you often model or predict the IR frequency of compounds. And nowadays we can do this pretty well. There are some other things that affect this. And again, this isn't too important. I just want to point it out. One is hybridization. We'll see this effect later on, right? If we have this CH triple bond or this CH single bond, right? They're both CH single bonds, but then the carbon, the hybridization of this carbon, right? This is an sp bond. This is an sp3 bond, and this bond is actually shorter, which means that it's stronger. And so that'll occur around 3,300 centimeters. While this one is longer and weaker. And this will occur at approximately 2,900 inverse centimeters. Another thing that can have a factor is resonance. we can see the effects of resonance. So for example, this alkene right here, or this, my bad, carbonyl will absorb at 1720 inverse centimeters. Whereas this double bond will absorb at 1680. And we can resolve that, or we can think about that as resonance. So we can draw a resonance form here. And then we can kick over this double bond. And so we see that this positive charge is distributed over this carbon, and this carbon is distributed over 2 carbons, which has additional resonance structure. And so that means that this double bond isn't quite as strong and thus absorbs at a lower frequency. You don't really have to know too much of this stuff. You can actually learn a lot from IR. There's a lot of intense detail that you can grab from IR, but we're just going to focus on the basics. And that's not just because we're in intro class. It's because IR was something that was extremely useful back in the past, but now we have better instrumentation. Or we'll call them better tools. And so there's still stuff that we grab from IR spectroscopy. We still use it, but we don't use it for the super complex stuff. We just use it for the more stuff, right? The better tool that we're going to learn about later on is NMR. That's really going to be the star of the show.